Okay, so here we have our general power supply design. To begin with, we have an input of 120 volt AC signal that we're sending into a transformer that's stepping down that signal to a 16 volt AC signal. Now this signal is taken and sent into the rectifier, which takes all the negative voltage and turns it into a positive potential voltage. This signal is sent into our filter that smooths out the signal, but it still has some sort of ripple. Now, to reduce this ripple, we'll be using a very large capacitor to make it look more like a DC signal. This signal will be sent into our regulator, which will smooth out the signal and make it look like a DC signal. And that signal will be sent to our load or to our output, where we can measure that value. Now, for the specifications of our lab, or our design, we were told to change the output voltage from 5 volts to 10 volts. We will be using a potentiometer to hold that voltage and to change it from 5 to 10. So this is the formula that we used to decide which values we wanted to use for R1 and R2. We knew that our Zener voltage was 5 volts, and we knew that we had to have our output voltage range from 5 volts to 10 volts. With that in mind, we decided to choose 100 k ohms for our R1 value and a 100 k pot in series with a 6.3 k ohm resistor for our R2. So when our output voltage is 5 volts, our potentiometer is 0 ohms, but it's also in series with a 6.3 k ohm resistor to hold the output at 5 volts. When our output is 10 volts, our potentiometer is set to 100 k ohms.
So if you look here, you'll see our transformer that steps 120 RMS voltage down to about, it should step it down to 12, but it really steps it down to about 20-ish. You can see that we've soldered wires on to either side and wrapped them in electrical tape. This is our neutral. We just wrapped it up in electrical tape so it doesn't touch anything in our circuit while we're working on it. If I plug it in, we can see that it's running power into our top rail up here, which is going into our rectifier and then into our filter. If you look over here at our schematic, this is this portion. You can see our 680 microfarad cap right here, and we actually reduced the size of the resistor right here so that it was 1K. The purpose of this resistor is just to dump current when you unplug. So if you watch as I unplug this, you'll see that we're dumping current in our cap. That's so nobody gets shocked. Go ahead and plug it back in. We'll look further into the circuit. Right here, we can see a Zener diode that holds the input of our LM741 op amp. It's holding it around 5 volts right here. Then we have our transistor network. This is our Q1 right here. This is our Q2, looking at our schematic over here. This little portion right here is a short circuit protection. We also have a 1 ohm resistor right there that senses the current going through the network. If we look at our output right here, we'll see that it's at 10 volts, and if you look over at our potentiometer right here, this represents our R2 value in our circuit. And as we reduce this down to 63K, we'll see our output voltage drop to 5 volts. So when I twist this potentiometer down, see the voltage drop down to 5, and I twist it back up, we're back up to 10. In this video, we're showing you that our current across our 1 ohm resistor right here is 480 milliamps. We just noticed that we missed that in our last video, so there you are. So this is our project update. This is our final update that we did. We did 3 updates throughout the course of making our power supply. We used this to keep track of how our progress was doing, and it would keep track of what we did prior so we could see what we were doing wrong and help improve on what we were going for. This is our schematic of our power supply. You've already seen this. When we first started, this had no values in it in our first update. We got our general topology down, and then once we did that, in our second update, we added some values. We calculated our R2, R1. We kind of tested with some of these values after our op amp. We kind of had to do a bunch of simulations to figure out those values and ask around to figure out exactly what their purposes were. When we first began the project, we thought that this transistor value would be an okay one. As soon as we started our experimentation, we found out that that wasn't the case, and it immediately burned up. So we had to find a transistor that had a higher rating. After doing all this, that helped us develop a parts list.
So for our parts list, it shows all the components that we use to build our power supply and get it running. And we had to use a 25-watt power resistor at 20 ohms for our load. And we also used 2 power BJTs, the TIP318s, because those are rated for 3 amps, and it worked exactly with what we needed. We used a NT rectifier, and we also used a transformer that stepped down from 8 to 1. We used 680 microfarad capacitors. We also used a Zener diode. Here we have it listed as a 5-volt breakdown voltage Zener diode, but we managed to only find one that was 4.7 volts, but it seemed to work fine with our power supply. We used a basic universal LM741 op amp, and we also used a 100K ohm potentiometer. Most of these components we managed to purchase from Fry's Electronics, but you could also get most of these components from DigiKey or JMCO. So we needed to come up with a method to test the functionality of the power supply. So this right here is a general overview of what to prove the functionality of the power supply. So to begin with, we decided to test the output of the transformer to confirm that it was similar to the simulated values. After we've confirmed that we had similar values to our simulations, we decided to build the attenuator. And then we measured the output of the attenuator to see if it also compared similarly to the simulated values. The next step was to build and test the regulator. And once we got the regulator working, we hooked it up to a potentiometer and a load, and we used the potentiometer to observe the different changes in the output of the power supply.
So right here you can see our simulations for our transformer. The green waveform is the waveform for the power coming from the wall. It's listed at 170, but that's because that's its true value, and its RMS value is 120. You can see on our blue waveform, this is the output of the transformer. That came out to be around 16 volts. You'll see that in our next slide. This green value is our output of our transformer, and the blue is the output of our attenuator. So as you can see, our attenuator takes our transform wave and makes it closer to DC. It has a ripple of about 4 volts. When we experimentally did this, our ripple was much, much smaller. It was almost DC voltage.
So here we have the waveform of our regulator. So as you can see here, there's a transient state, and the output managed to reach at 10 volts. This specific waveform, the 10 volt output DC was achieved using or when the pot was set to 100K ohms, and then the 5 volt DC value was achieved when the pot was set to 0 ohms. Thank you.